Hello everyone, on today's video we will be going through the material balance of a batch reactor. A batch reactor is a reactor with a constant volume where the reactants are added at the beginning. It has no inlet flow or outlet flow, making it non-continuous. So let's start with the mole balance. The mole balance, so the moles going in minus the moles coming out plus moles being generated inside the reactor, or in case if it's being consumed, it will be minus consumption, equals accumulation. Now since there's no inlet flow or outlet flow of the reactor, these two will be 0, leaving us with generation equals accumulation. Now, generation equals rate of reaction times volume, where the accumulation equals the change in moles over the change in time. We'll sub these two back to this equation, and we'll be left with RA times V equals change in moles over change in time. Rate of reaction could be given in different forms based on your problem statement. It could be given in a first order, like this, negative K Ca. It's negative because that's first order. It's negative because A is a reactant being consumed. K is a reaction rate constant, which depends on temperature, meaning that if the temperature is constant, if it's isothermal, K is constant. If temperature is varying, also K will be a function of temperature. But in most problem statements, you'll find yourself working with an isothermal batch reactor, meaning that K is constant because temperature is constant. So back to the rate of reaction, it can also be given in second order, where the concentration is to the power of 2. And that's usually because your stoichiometry of your function, chemical reaction was 2A will give you, for example, B. So that order here is based on your stoichiometry in the chemical reaction. It could be also a mix of reactants. So it could be like negative K Ca Cb, and that is also because of the chemical reaction. That's because you had a chemical reaction like this. A plus B give you C plus D. These two here are based on your reactants there. For the simplicity of this video, excuse me, we will use this reaction rate. Sub it back into this equation here. So negative K Ca times the volume equals change in moles over change in time. Now this differential here is in terms of moles. We need to change it to be in terms of concentration. So concentration equals moles over volume. If we further rearrange that, we'll get Na equals concentration times volume. We'll sub this to this differential here. So the right side will be dCAV over changing time. The left side will stay as it is, negative K CAV. Now, this volume is constant, as we said earlier. That means we can take it outside of the differential. we'll be left with volume times differential of CA over changing time. The left side will stay the same, negative K CAV. Now we can cancel both these volumes. We'll be left with negative K CA equals change in CA over changing concentration over change in time. We'll rearrange this equation a little bit. We'll take dt to this side and CA to that side. We'll be left with negative K times dt equals 1 over CA dCA. We'll integrate both sides, and this side will be from 0 to t times 0 to the time we're looking for. Now on this side it will be from the initial concentration to the final. If you have a problem understanding this integral part of the video, I'll make another video to explain the integrals in reactor design, going through common examples that you'll see. But to continue on with this differential, on the left side you'll be left with negative KT equals right side ln CA over C naught. In order to get rid of the ln, you'll put both sides to the power of E. This is gone, so you'll be left with E to the power of KT equals CA over CA naught. If you rearrange it, you'll end up with concentration of A as a function of time equals E to the power of negative KT times the initial concentration. And that is your final equation. You can use it to find any concentration at any moment of time. We'll do another video where we can use this equation in an example. Till the next video.